Hello. Thank you for being here for the 24th edition of the Computer Vision Meetup Paris. Before we start, a few words about the hosting company, which is Sikama. We're a startup company from the Theodore Group, which is located 10 minutes from here, which is where the second speaker actually is right now. He's joining us shortly. So we are a data science and data engineering company, and we have organized the Computer Vision Meetup in Paris for a few years. It's always been a fun and interesting flow of ideas. There has been a lot of startups, industries, and researchers, also a lot of interesting projects presented here in Computer Vision. In Computer Vision, we have a close link between industry and research. And tonight we host two eminent researchers are with us. So firstly we have Arthur from DeepMind, who is going to talk to us about continual learning and the Nevis 22 benchmark, which is a benchmark of I think of 100 tasks of computer vision with a great variety of tasks. And secondly, Hugo, who will join us, will talk to us about the link between architecture and training strategies in computer vision, especially with the recent development of vision transformers. The floor is yours.
Thank you. So thanks for the invitation. Very nice to come back to Paris. So thank you all for being here. Today I will present you the Nevis 22 benchmark. So it's a project that thanks to all these fantastic people across DeepMind, across multiple time zones and teams. So first of all, so the typical life of an ML practitioner that I think most of you know is like you're gonna have to look at data. You're gonna take ideas or code on internet, on GitHub, Face or whatever. Then you're gonna make a lot of experiments, a lot of failure, a lot of wasted compute and experiments, and then you're gonna have a result. The only problem, furthermore, you also have like a continual aspect as you're gonna share ideas and models with other people. So for example, you could take a model, you could train it from scratch, then you could upload it on a Face, then you will someone else, one of your friends, is gonna download it, fine-tune it for a new task, and then upload it again. So it's very social in a continuous learning way, where everyone is gonna collaborate together to add multiple tasks to your model. However, the only problem is that right now we don't really take that in account. So what we do, we're gonna take a model, we're gonna train it from scratch on a big, maybe pre-training data sets, so a lot of subset supervision, for example. It can be very costly. And then we're going to have a deployment phase, either by you or someone else, where you're going to fine-tune it on other datasets. For example, like here, cat versus dogs. This is fine, but then at some point, maybe you're going to expand your model. So you don't want a ResNet anymore, you want a VIT, sure. You don't want to pre-train on ImageNet, you want to pre-train on the GFT or ImageNet 22K, sure. So you're going to do a new training phase. A new pre-training phase is going to be very costly. It's going to take maybe weeks, it's going to take hundreds of GPUs. And then you're gonna have a new deployment phase for a new downstream task. The only problem is you're gonna have multiple times retraining from scratch. So everyone for a new model, they retrain from scratch everything, which is very costly. And the continual learning dream would be to be able to leverage what we learned before. We don't want to waste any compute, we don't want to waste any information. We want to keep reusing what we did before in a way or another to always improve the learning of the new task, of the new data. So you could imagine like this, we could start with a very small model, and then we train on an easy task, cat versus dog, and then we fine-tune it, we add maybe new data, we maybe expand the model, and we add a new task, a new configuration, to always have a new model, train on new data, and to never have to retrain from scratch and to wait compute and information. That's our dream. So of course it's the bold dream of continual learning. It's a field since 20 years, it's very hard and we don't really know how to do it efficiently yet. There is a lot of open questions. Two open questions we're going to focus on this talk is what kind of data and experimental setting we want to have. So it's very important not to avoid any leakage of information among all the tasks, between the past task and the future task. and which kind of metric is interesting in order to measure this kind of behavior of the content learning system. It's not training one task, it's training a sequence of tasks. To do so, we present the never-ending visual classification stream, Nevis 2022, which could then improve them. In this setting, we want to propose a benchmark with a sequential amount of tasks that we're gonna train them sequentially, one after the other. We want to be able to never waste compute, therefore we want to have some kind of forward transfer by always improving the learning efficiency on the new task by exploiting what you learned before. And plus, we don't care only about the accuracy, but we also care about the number of flops, how much data, and how much computation you use. So, in order to construct the Nevis datasets, the benchmark, we first selected multiple computer vision proceedings, so that you may know, CVPR, SCCV, ECCV, and BMDC. From this proceeding, we took 3 decades of it, from 1992 to 2021. We sort them chronologically, and for each year, we sample 90 paper, around 90 paper. Then, among these 90 paper, we can select only the paper that use the datasets with image classification, or something that can be corresponding to image classification, for example, continuum. Then, we're gonna do some filtering. So not everything can be useful. Sometimes for all datasets, data is not available anymore. There is problem of license type, and there can be duplicates or slight duplicates between datasets, so we want to avoid that. So we do a lot of filtering, and in the end, we have 106 tasks in total. So each task is a dataset. We have 8 million images coming from many domains. So as you can see on the GIF, you can see a sample of all these domains. They are very different, as you can see also on the bottom right. So you can see the distribution of each domain per year. We can have things from medical, so X-ray or other medical. We can have counting, we can have OCR, texture, object, face, or satellite. So it's a very wide variety. And what is also interesting is some kind of domain are gonna arise at some point, like texture maybe, and then gonna disappear another year, and will only come back a few years later. So there's also some kind of periodicity of the domains. You can see on the bottom left the amount of data per datasets and accumulated amount. Obviously, the latest years, the closest year are more, the latest datasets are more samples. We did this dataset that way, by doing some chronological way, because it corresponds to what practitioner will have in real life. You're going to train a model right now on some datasets, but later in 1 year, there are going to be new datasets, so you want to use that, and etc. So we want to be simple in a way to construct this benchmark. It can be reproducible. It's unbiased to task selection, which is a very big problem in content learning. And furthermore, it's quite large scale compared to existing datasets in content learning. You can see here an example of the task in Nevis. So there is very old datasets, such as Aberdeen or Magellan. There is also MNIST, but there's also ImageNet, or even COCO. So there is a very bit of everything. Now we also want to focus on the metrics. So to limit here, we're gonna only mention 2 metrics: the average error, that we want to minimize, and there's also the cumulative flops. So the flops is the amount of compute we're gonna use. We want to use the cumulative flops, so it's the number of flops that we use across all tasks of the stream. Furthermore, this number of flops, we also consider the flops used during the cross-validation and the hyperparameter tuning. Usually people, when they choose the flops, they only say the flops of one training set, one training run. But in a way, it's not realistic, as an ML practitioner is also going to have to do many cross-validation, many parameter tuning. And this is also important, so we want also to be efficient in this way. In the end, we're going to have a Pareto front. So on the x-axis, we're going to have the compute that we want ideally to minimize because we don't have infinite compute. On the y-axis, we have the error that we definitely want to minimize. The best learner would be a model that will be on the bottom left. We're using very little compute to have a little error. And likewise, the worst learner will have a lot of compute for very bad results. We have a Pareto front because you can imagine that for one learner, you could allocate more or less compute. For example, you could just give more epochs to do, or more extensive hyperparameter tuning that lead to more compute, but also lower error. So it's a trade-off. In the protocol, so we have 106 datasets in the task. We're going to split it in 2 sets. The meta train from 1992 to 2018, sorry, and the meta test for the remaining years. in this setting of the split, we're going to first focus on the meta train. We're going to do 2 levels of hypermeter tuning. For the hypermeter tuning, we're going to focus on 2 metrics, the error and the flops, that we both want to minimize ideally. First, we have the classical tuning at the task level hyperparameters. So for each task, we test the task validation sets, and we do some hypermeter tuning to find, for example, the optimal learning rate or the optimal number of epochs. So this is specific to one task. Then we can also have a tuning at the stream level. So this is hypermeters that we want to be shared across all tasks of the stream. So therefore, we need to measure it. We're going to take, for example, here 4 tasks of the meta train, and we're going to have a fake validation task made of the 2 remaining tasks of the meta train. So we don't see the meta test, of course. And it is in this case of the stream level hypermeter tuning, we can find, for example, what kind of model architecture we want. Do we want a ResNet 18 or ResNet 34? I don't know. Do we want also to have different kind of hypermeter search? Maybe we want to limit some kind of a range of learning rate for each then subsequent data sets. That's something that we can record here. Then, once we were able to find the optimal parameters, we find the best model that we train on the meta train. We're then going to train on the meta test. And the meta test, we're going to train on the train set of the meta test, and then evaluate on the test set of the meta test, of course. We then focus on 2 metrics, the error of the meta test and the cumulated flops of the union of the meta test and the meta train. Because the meta train were also a thing that we train on, and we also want to minimize this number of flops. So number of flops is really important in the Pareto flops. Now we can see some results. So first we have some baseline. So a very basic baseline would be the independent. In this independent, we're going to train 1 model per task independently. So the nice thing about it is we do it in parallel, so it's very efficient if we have a lot of GPU. For each model, we can initialize randomly, whether with the same random seed or another random seed, and we're going to train them completely independent. Then we have the fine-tuning. So the fine-tuning that everyone knows. We can have a naive fine-tuning where for the task 3, for example, we fine-tune the task 3 from the task 2, that is fine-tuned from task 1. Or we can do something a bit smarter. We can initialize the task 3 model from the most relevant task of the previous task. So this notion of task relevancy is quite often seen in the literature. Here we choose a simple method but efficient. We simply extract the features of the task 3 data using the model of task 1 and task 2, so the previously learned model. Then we're going to compute the KNN accuracy, so it's a very basic surrogate for which features could be useful. Then we select the model with the highest KNN accuracy on task 3. It's always on the validation set, of course, on the task 3. And then we're going to use that as initialization for the new model of model 3. And the third and last baseline is a multitask training, where we have a shared backbone. So for example, it's the same ResNet that we can be trained on parallel on all tasks. We can have 1 head, 1 classifier per task, and we can train them all in parallel. So obviously this one is a bit less efficient, as it has access to everything, but there's also a better sharing of information. And there's also a big problem in this case of multitask learning, where you have different kind of data sets, for example, MNIST and ImageNet, where one data set has very little data, another a lot of data, and there is always the notion of how to balance how much data do you want to allocate. Do we want to have a uniform sampling or something a bit smarter, which is very hard to define. So now we have a Pareto flop. So on the y-axis we have the average error, on the x-axis we have the flops, the cumulated flops. So for each point, it's a lot of hypermeter tuning and for a lot of tasks. So therefore we have 1,700 experiments per point. We have a Pareto flop because for each, for example, for the fine-tuning dynamic, so the fine-tuning from the most relevant model, you can have multiple points as we can allocate for each point more epochs or more extensive hypermeter tuning. So one thing that is kind of obvious is the more flops that we have, meaning that we have more extensive tuning, we can find a better model which will result in a lower error. So that is normal. Okay, so we have a little interlude. I hope you get a drink in between. So about the Pareto flops. So of course it's going to take quite a lot of compute. We propose also different kind of substream if you don't have as much compute, luckily. On the left part, these points are limited to around 4 days on a single GPU. On the left part is more like in the 100 of days of compute on a single GPU. Of course, ideally, you have multiple GPU to do so. We're going to focus on the part on the right. So now we have the interesting results. So the fine-tuning from the most relevant, so the one we choose which one was the most relevant model, is the one who provided the best Pareto front. That's why it's kind of simplicity. And also, which is obvious, is that you can see that there's a significant improvement brought by the fine-tuning compared to the independent. So independent can be trained in parallel, so it's very useful if you have a lot of computes in parallel. Where the fine-tuning, it has to be sequential, as you have to train sequentially one after the other. But you can find the fine-tuning, because it does some kind of knowledge sharing. By having the knowledge from the previous task, you can find that for a single given flop compute, so if you slice on the x-axis, you can find that we have a much better performance with the fine-tuning than with the independent model. You can also find other models, like for example the BHPO, so it's a Bayesian optimization, it's a pink star, which has better result than the independent, but also use much more compute, so it's also not very useful. And in the purple, you can find fine-tuning dynamic, but where before doing the training on the navy stream, we have a big pre-training on other datasets. So for example, datasets such as Align, which is a very big dataset, which then provide much better error, but also we have to take in account that this pre-training on Align, for example, has some huge amount of flops, which is one order of magnitude more. So that's a trade-off that you have to take in account. Yes, that's what I was saying. Then, if you look at only those pre-trained models, you can think that these pre-trained models are very useful. So maybe we can just fine-tune them independently, not sequentially, and that's enough. And actually, no, you can find here, so both of these points in red and blue are both pre-trained from a large model. So it's basically the model that was trained for Flamingo. And you can find that fine-tuning from the most relevant task in Nevis after doing this initial pre-training is still more beneficial than simply fine-tuning and then training independently. So even with the best model that you can download on Hugging Face or whatever website, you still maybe want to have some kind of knowledge sharing among all your tasks that you have. So this is a very good news for us. And you can find here a plot of all the relevancy of the task. So an arrow from A to B means that the task B was fine-tuned from the most relevant task, which is A. So you can find here a graph, and each color corresponds to a domain. So in yellow, it's kind of a generalistic object domain, such as ImageNet, but you're going to have also other colors for texture, satellite imagery, or medical. So you can find some clusterings by color, so which is quite obvious that we can find this kind of correlation where maybe the most relevant model is a model that was trained on the same kind of domain. Furthermore, you can find several hubs, for example Caltech 101 or Caltech 256, but also other domains such as ImageNet and Sketch. So you can find that ImageNet is obviously the biggest hub, which is also something that maybe not surprise you, as in computer vision, a lot of people, when they fine-tune a model, they're just going to take a model that was pre-trained on ImageNet. ImageNet is quite wide, more than 1 million images, and quite diverse also, with a lot of classes, more than 1,000. And although there is a lot of dogs and cats on these datasets, it's still a very beneficial dataset. However, maybe only using ImageNet is not what you want, because you can find that you can have even longer chain. For example, Sun Attribute, which is one of the longer chain we had, has more than 7 datasets that were trained sequentially, meaning that only training from ImageNet was not the best performance, and maybe we wanted to have a continual learning procedure where we're sharing information from the most oldest datasets and recursively going towards Sun Attributes. So this is also a very good news for us, that we can find that having more knowledge transfer, having a continual learning procedure, and can beneficial to further improve our model. And you can find here also a fine-tuning chain, this time not with simply a fine-tuning, but fine-tuning first from a pre-training model, so big pre-training model. You can find that it's a little bit less depth, because simply fine-tuning from this big pre-training model is also very beneficial, but we still have several chains of more than 2 or 3 tasks, meaning that even with the best pre-trained model available, you still want to do continual learning, for once to reduce the number of flops, but also to improve the performance, both of them. And we still have the clustering per domain. We can also find analysis by domain, for example, a medical domain, object, or OCR. And a very interesting finding is that the model ranking will strongly depend on the domain, meaning that you cannot have one model for everything. You may want to have different kind of model, maybe different kind of architecture, maybe different kind of range of optimization or loss, but you want to have different kind of specialization per domain. And this is where having some kind of automatized setting, like the one we propose in this benchmark, to find the best hyperparameter, the best model, is very useful in order to automatize the cycle life of ML practitioner, to be able to adapt quickly and efficiently on any kind of domain. We can find also like the rule rate. So here we measure it not the average error, but rather the cumulative relative error. So the zero slope is the independent baseline. So if you have zero, you don't have any improvement compared to independent, which has no sharing of information, which is obviously not what we want. So we want to do better than that. So we don't want obviously a high positive slope where we do worse than the independent baseline, and a negative baseline will have a lower error than the independent baseline. You can find that all models improve over it. The fine-tuning in green further improve it, and the pre-training, that we do a pre-training from the Flamingo model and then we do a fine-tuning, even further improve. Unfortunately, this is not enough, because what we can find, each of them still improve continuously across time, meaning that doing control learning instead of doing independent as everyone is doing control learning is beneficial, but it's still not as good as we wanted, as we want to build a learner that learns faster and faster across time. As yourself, as a human, when you learn several tasks and then you cross a new task, you should be able to learn it even more efficiently, even more quicker. And this is not what we can find yet in the research. And our dream will be to have some kind of a Pareto front like this, where the learner are more efficient the more you learn tasks. This efficiency, you can measure it with forward transfer. So basically the forward transfer is to measure it that if you learn one dataset, and then you see again the same datasets, you should be able to learn it even faster and more efficiently than before, because you already saw it once. So in Nevis, we have 9 tasks, 9 datasets, that actually appear twice in the stream. So we can measure it with forward transfer. So we can find here the forward transfer. So obviously for independent baseline, the forward transfer is 0, because there is no knowledge or no sharing of the knowledge. And then we can find here the fine-tuning from the previous model, which is kind of naive fine-tuning, or in orange, the fine-tuning from the most relevant model. And we can find that both, in almost all situations, will have a positive forward transfer, meaning that the second time the fine-tuning encounter a task, it learns faster. And this is a metric that we want to further improve it. As the more time you see similar task, or even the same task, you should learn it even more faster in order to have exponentially increase of efficiency compared to the flops you use. And finally, another point, for those who know control learning, a lot of people in control learning, the biggest benchmark that even I did in my PhD is a split ImageNet. So basically you take ImageNet made of 1,000 classes and you split it, for example, in 10 tasks, each made of 100 classes. And then you learn them sequentially. The only problem is this is not very relevant to the actual practitioner in reality, because all the tasks are very similar. It's more or less the same kind of data sets. ImageNet have a lot of dogs, for example, on cat, so they may be dispersed across all tasks, so it's almost IAD. And you can find here that the conclusion between the different baseline, independent, fine-tuning, multitask, are rather different from the conclusion that we had on Nevis, and that with given enough compute, all the baseline are more or less the same performance, meaning that we can already not show that there is a knowledge transfer or even a forward transfer, meaning that people, we believe that we shouldn't evaluate anymore on split ImageNet, as it's a benchmark. It is maybe nice for academia, but it maybe doesn't translate to actual gain in the reality, where you have different kind of tasks, different kind of data, and you have a distribution shift between domains. So for the conclusion, so efficiency is a very important metric for us. We want it to be a first-class citizen. We don't want to waste compute anymore, so we will always want to retrain, to fine-tune the model from the previous initialization. And therefore, we want to have a forward transfer to further improve this efficiency. And this efficiency can only be done with realistic benchmark if we want to actually translate those gains in reality. To do so, we need to have some kind of natural construction of the task that we believe that we did in Nevis. This restructure of the task should be reflected both because we have enough domain to correspond to what maybe could be the domain that you have to do in your real life. And it's also helpful in order to generalize to new tasks in order to learn more efficiently. Furthermore, we want to be agnostic to the method. The only requirement is to be able to scale. More efficient method, maybe bigger model, should be able to scale more efficiently given the same amount of loss. And finally, the two best baselines we found, so pre-training is useful, but it's not enough, and we find that we can further improve it with the fine-tuning. Fine-tuning, which is usually the weakest baseline in a classical benchmark in control learning. Here we find that actually fine-tuning is a very efficient benchmark, despite its simplicity. And the fine-tuning from the most relevant method, which is a slight variation of the fine-tuning from the previous model, is even more efficient. The Nevis benchmark is not a solution, it's a proposition to find a solution. There is a lot of open research question. Maybe how can we efficiently learn a never-ending learning system? Can we improve this efficiency, even when scaled to larger model? Another aspect that is, I think, worth considering is how to modularize. If you have some kind of modular network, where you can have different modules, maybe trained in parallel on different kind of task or domain, could we then gain this knowledge to have some kind of composition of modules in order to have this kind of forward transfer? There's also other question, maybe also how to grow your model. Right now, we had some parameter tuning to find the best model size, but then our model is fixed across time, which is not realistic in real life, because in real life, maybe you want previously to use a ResNet 18, then a ResNet 50, and then you want to use a VAT, and maybe tomorrow another model. Can we maybe grow this model? Can we expand it? Can we change completely the architecture, but still retain some of this knowledge from this model? And this is an open question that even knowledge utilization is not really working right now for it. And there is much more other question, like if you want to update your knowledge, if you're talking to a chatbot, you want to give maybe say some information about you, what is the dog name, and then you expect the chatbot to be able to remember that. So how to update this knowledge very efficiently and quickly. What kind of memory do you want? Do we want to remember everything from the past, or do we want to have some kind of graceful forgetting? So thank you for listening to me. You can find the archive on this link, and we also have the benchmark that is available on both JAX and PyTorch. That's it. Do you have any question?
Two questions. The first one, in the meta test, why is the meta test not the same as the sample from the same period as the meta train? Why is it only from 2019 to 2021?
This is a very good question. So for the meta train, we choose the years from 1982 to 2018, and then the meta test are the remaining years. And why do we choose this meta test in these remaining years and not maybe sample uniformly across the whole stream? And the question is like we want to avoid any kind of leakage of information. So we want to be able to design a model with all the parameter tuning that is efficient currently, and then maybe next day you're gonna have to train on your new task. And when this task arises, you want to take your method with your maybe set of parameter, your set of model, and then just simply put it on this new data set, which is new, so in the latest year, and you want it to be able to perform efficiently.
And the last one is for given. So the last question is for given.
For a given model, at which number of new datasets does the model start to forget?
So the question is, when do we start to forget? So in control learning, classically, for example in class incremental, where we learn, for example, multiple subsets of ImageNet continuously, usually we want to learn continuously the new subsets, and then we evaluate every time or at the end on all previous subsets that we don't want to forget. In this situation, we don't really care about it, as maybe it's some kind of artificial setting to want to this forgetting. As in practice, you're gonna have a model, and then you're simply gonna copy it for the new task. And therefore, for the previous task, the task maybe of the past, you're simply gonna keep the previous copy that didn't see the future. So in a way, you never have to, the model of 2021 is not gonna be evaluated anymore on the model, on the dataset from the previous past. Does that make sense for you? So previously, we had only a single model. This model was continuously updated, and therefore, this single model was then evaluated on the new task, but also the past task. But in practice, that's not what you want. If we take, for example, the example of Hugging Face, so the Hugging Face Hub, you have different models that you can upload. What you're gonna do, you're gonna have first maybe BERT that was pre-trained on some datasets. You can use it. It's very efficient on BERT, on these datasets. Then you're gonna download it, you're gonna fine tune it for dataset B, it's gonna be very efficient for dataset B, and you're gonna upload this new version on Hub. And basically you're gonna have in your Hub two versions, the old version that is very efficient for dataset A, and the new version B, which is efficient for dataset B, and that have gained information from A, but you don't care about its performance on the previous datasets. So because basically the big notion in control learning where we have a single model is based on the assumption that we have a very limited amount of memory maybe, and you cannot have a lot of models, but in practice it's not really true, as your disk space is quite large enough to have many models in parallel, even just on disk.
And did we find a sequence of datasets that are smaller but can train faster to reach, for example, performance for ImageNet, something like this?
I think I have a table for that. No, I don't have a table for it. So basically, what we found is in general, if we were limiting ourselves to small datasets, we would have a lower performance. So actually having a bigger dataset with more diversity, inter-diversity, usually more beneficial. So we don't really have this. We did find that ImageNet is a very relevant dataset. So if we remove dataset from the stream, we do lower the performance, but not that much. And usually, as you can find also on this one, that ImageNet is a very important dataset. But you can find that a lot of tasks also are outside of the node of ImageNet. That you can remove it without too much or loss of performance.
The reason that ImageNet is very important is because it's the first dataset vision.
The image is important because there's a lot of images, more than 1 million, and a lot of classes, so more diversity. I don't know,
maybe I don't understand properly, but for me, it should be that, for example, imagine that previously we had another dataset, ImageNet, some kind of ImageNet, because all the other model depends on this one, but it was the first dataset. So maybe it's the reason that one is important.
So you mean that all methods were optimized for these datasets, and then it decoupled that it make it better. This is a problem that is way harder to. So basically, the question is maybe ImageNet is a dataset that was so big that everyone is using ImageNet and everyone is creating a model that performs well on ImageNet. So there is intrinsically in the definition of the model there is a bias to this. You can find that also with Adam, the optimizer. Everyone is using Adam, so maybe all the methods are working well with Adam, but they're working poorly with other optimizer who may be better. So you may fall in a local minima with the ImageNet, and that is true, but it's much harder to find if it's true or not, because we have to redo all the research again without ImageNet. That's an open question.
Okay, thank you, Arthur. It's now time to move to the presentation of Hugo, who joined us.
Hello everyone. So today we'll talk about architecture and training for visual understanding. I'm Hugo from Material Research. I'm currently a research scientist at FAIR, and I was previously working on computer vision, so today we'll talk about computer vision. Generally, when we talk about computer vision, we have in mind different kind of tasks. We can have image classification, object detection, semantic segmentation, or instance segmentation. There is also some other tasks. Today, I will mainly focus on image classification because generally, when we propose a new method, we apply this method on image classification and ImageNet, and it's possible to readapt after that the network and other tasks. So the method I will present are designed on ImageNet, but it's easily possible to readapt this method to other tasks. For instance, you can just add some component on top of the network to adapt the network for object detection or semantic segmentation. So I will focus on image classification, but it's possible to reuse that on other tasks. So today I will talk about different topics that are closely related to each other. The first one is train test discrepancy. After that I will talk about architecture for computer vision. And finally, I will talk about architecture and training interaction. So, the trend test discrepancy. There is different kind of discrepancy. Today I will focus on the label granularity. And the question here is, can we learn fine-grained image representation with coarse labels? Because you can have different granularity in one data set. You can have granularity like the first row, for instance. Here you can have cars, co. It's quite easy to collect data like that because you don't need to have an expert knowledge to label this data. It's quite easy without an expert knowledge to distinguish a car from a co or co from a bird. You can have some data with more granularity. For instance, in the second row, we focus on just some bird species, but here it's in fact not very hard to distinguish between these species. For instance, you can focus on the color to distinguish between them. So, generally, this is maybe not super expensive to collect this kind of data, but one kind of data that can be very interesting is when we have some species very close to each other, because if you look at the last row, in that case you need to have an expert knowledge to annotate this data. So in practice it's very expensive, and in practice generally when we want to solve an hard task we have this kind of data, or we want this kind of data, but this is not very easy to collect and annotate this data. So we propose Graphit, and the goal of Graphit is to learn and find out granularities than the one provided by the label. So typically learn with the first row and being able to classify data like the data in the last row. To evaluate this method, we propose 3 different tasks: category level retrieval, on-the-fly classification, and the classical transfer learning on fine-grained dataset. So the first task, coarse to fine category level retrieval. The idea is very simple. You train on coarse levels. For instance, these 3 different coarse levels. Pyrgus, it's a kind of butterfly. To be precise, it's an order of butterfly. An order in the phylogenical hierarchy, it's a group of species. And for instance, in Pyrgus, you can have these different species. And in this example, the different species are the finest level. So the idea is very simple. You take one images in the test set, and you rank all the images in the training set, and you compute a map on the final granularity. So it's a good ranking if you are able to rank in the first position the images of the same species. For instance, you can see here with Graphit in the first rank, we have images from the final granularity, but at train time, the network was just trained on this coarse level. The second task is just a KNN classification. So at test time, we apply a KNN classification on the final granularity. And the third task is the classical transfer learning, so I don't do a slide for that because it's just a full fine-tuning of the network on the final category. Here, this is a figure of the Graphit training architecture. I say training architecture because some components are specific for the training. This training architecture is not very complex. This is 2 main ideas. The first idea is to say, okay, which kind of signal we can exploit to be able to classify at a finer granularity. The first one is the coarse labels. So to exploit the coarse labels, this is the classical supervised learning. This is the yellow part in the model. We don't use directly the cross entropy because, if you remember, the task number 2 is KNN classification. So we use a loss suitable for KNN classification. Here, this is a SNCA loss. In SNCA loss, we exploit the memory of the embedding of the training images. This is the hem here. And we have different projectors to readapt the feature of the model. For instance, F theta here, it's a ResNet 50, P theta it's an MLP, Q theta it's an MLP, and the idea is just to refine the feature of the model to make suitable this feature for the KNN classifier part. The second signal is to say, okay, maybe we can say each image is in its own places. So it's quite similar to self-supervised learning. And therefore we use the BIOL method. And the blue part, it's an exponential moving average of the model. So to update the blue part, we use this formula, that is an exponential moving average of the model during the training. And we use that with an instance loss. So the idea is to be able to have an embedding very close from each other for the same images with different data augmentation. So for each images, we take different data augmentation of these images, and we try to have the same embedding, the same representation in the network for these different data augmentation, and we try to have quite different embedding for different images. So the idea is to say, okay, each image is in all places. And because the idea is finer category I between these both concepts. It's between course levels and each image is in all places. So here it's an ablation of the different graphic training components. And as you can see, the main improvements are related to the use of both loss. So if you use just supervised learning or just instance loss, it doesn't work very well. It's better to use these both similar. So the question, can we learn timeline image representation with course levels? The answer is yes. For instance, with graphic by experimenting jointly self-supervised and supervised learning and train time. Now I'll talk about architecture for computer vision. The 3 October 2020, a lot of people asked if this is the end of convolution. Because there is a major paper, an image is worth 16 by 16 words transformer for image recognition at scale. In this paper, they are able to reach state-of-the-art performance on ImageNet classification benchmark with the pure transformer architecture. This is the first time non-convolutional architecture reached state-of-the-art performance on this benchmark. And this is a very interesting result because today transformers are the state-of-the-art architecture in many fields, for instance in text with BERT-like training or GPT, in speech, and now it happened in vision with the VIT paper. Before the VIT paper, there is a different attempt to incorporate some transformer mechanism in ConvNet. For instance, some people try to incorporate attention mechanism. This is the case in REST ST. Some people use hybrid architecture. This is the case in DAT, in DITER with object detection. And before this paper, some people try to apply transformer on images, but at the pixel level, and due to the quadratic complexity of the attention, it doesn't work very well. But there is a major drawback with vision transformer, because they require hundreds of millions of annotated images to reach ConvNet performance, at least GFT-like dataset. For example, GFT, it's 300 million images with 18,000 labels. It's a private dataset at Google. And if we compare that with the classical ImageNet benchmark, it's clearly bigger, and it's very hard for people to have a dataset similar to that. So in practice, except at Google, it's not possible to train just with this paper a transformer on ImageNet and reach state-of-the-art performance. So we try to answer this question: can we train an effective vision transformer model without a huge dataset like GFT? The idea is to say, okay, we don't have a lot of data, we have just ImageNet, but maybe we can simulate more data with a lot of data augmentation. But if you use a lot of data augmentation, maybe you can create some instability, create some bias, because data augmentation is not completely similar to have more images. There is less diversity, so maybe more risk of overfitting. So in addition to this different data augmentation, we add more regularization. And it's possible by finding the good combination of data augmentation and the good combination of regularization to reach very good performance on ImageNet with the transformer architecture just pre-trained on this dataset. The default training strategy is the first row, and you can see here we do an ablation on the different training components. The training is not very robust to big change in the training procedure. For instance, if you remove some kind of regularization, in that case the training doesn't converge. Another point with transformer, it's a very general architecture, and there is no hard bias related to deal with spatial input. For instance, with ConvNet, the convolution is very well designed to deal with images. So in transformer you don't have that, but the transformer is a very general architecture, and you can try to learn this bias in a soft way. So the idea here is to use distillation to learn that in a soft way. To do the distillation, we use the ConvNet in order to be able to learn with the transformer in the soft way the spatial bias of ConvNet, and as you can see, it works better to have ConvNet teacher. And we propose an additional distillation token in the architecture, and as you can see, it gives a small boost. Here, this is the comparison of the pure transformer architecture pre-trained on ImageNet and the state-of-the-art ConvNet on ImageNet. As you can see, we can have a similar performance. Here, this is just to explain how our distillation works, because we change a little bit the classical distillation strategy. Instead of using the soft output of the teacher, we use the hard output of the teacher. There is less information in that, but it's closer to the classical loss used for training transformer without distillation. So it's easier to have a convergence with this distillation strategy, and it works to use the hardness of the teacher. Because as we use strong data augmentation, the teacher can readapt the label according to the data augmentation, but this is not the case of the ground truth label. So for instance, if you have the first image, if you adapt random process crop, you can have this image, and if the ground truth label is zebra, here there is no zebra anymore in the image, but the ground truth label doesn't change, but the teacher is able to take this into account and to readjust the label in order to avoid some noise during the training. So, at the question, can we train an effective vision transformer model without a huge dataset like GFT? The answer is yes, if we use the right training strategy, the right data augmentation, and the right regularization. There is some related subsequent work that reuse the DIT training strategy in order to train new transformer architecture on ImageNet, in order to propose a new training strategy on this dataset. If we look at the Dozovitsky et al. Paper, we can see it's quite important to try to increase the depth of vision transformer in order to have a better trade-off in terms of accuracy and relative compute. So we try to do that with the DIT training strategy. We try to increase the depth of the transformer we pre-train on ImageNet, but it doesn't work because it's unstable. So now the question is how to train deeper vision transformers. The first idea is to say, okay, there is one method that is called stochastic depth, and the idea of stochastic depth is to randomly remove some layer during the training. So in a certain way, you can simulate a network with less layer. And if you adapt that according to the depth of the transformer, you can have a convergence in that case. So this is the first idea to train a deeper transformer. It's just to use stochastic depth with different coefficients according to the depth. But maybe it's not the optimal way to do that. If you look at NLP literature, there is different methods to train deeper transformer architecture. For instance, ReZero, FixUp, T-FixUp. The issue with this method is they remove layer norm, warm-up, and it's quite complicated method. But in that case, on image classification, on ImageNet with transformer, if you remove layer norm and warm-up, the method completely diverges. So we try to keep this, so we adapt a little bit this method, and in that case it works. But these methods are still very complicated. So we try to simplify that just by adding just by multiplying the output of each residual block by a diagonal matrix. And here the parameters of this diagonal matrix are learnable, and we call this method layer scale. And as you can see, it's a quite simple method, but it works quite well in comparison to a more complex one. We study the adaptation of stochastic depths according to the use of layer scale, and as you can see here, the optimal setting is to increase stochastic depth coefficient according to the depth of the model. So the question, how can we train deeper vision transformer? The answer is with layer scale and stochastic depths. So now we have trained transformer on ImageNet, we have trained deeper transformer on ImageNet, but if we look at the original transformers paper, we can see they completely changed the usual training strategy on ImageNet. They don't use SGG anymore, they use AdamW, they patchify the images. So maybe the training is quite important, maybe this is not the architecture. So now we try to answer the question, is attention necessary? To answer this question, we just remove all the self-attention in transformer architecture. We replace the self-attention by just a linear layer. So typically this architecture is an MLP. One advantage of MLP with linear layer for the spatial interaction, so this linear layer, it's you can visualize the weight of this linear layer in order to understand how the network deal with the images, which kind of operation are learned and which kind of operation are applied on the spatial dimension. And as you can see, the network learns some kind of convolution. At the beginning, this is convolution with small kernel, and the size of the kernel increase across the layer. So in the ablation, we have the classical MLP. The MLP I presented 2 slides ago. The performance are not too bad for a pure MLP on image classification, but transformers are still better. But something that is quite interesting is to say, okay, here we can see the network learned some kind of convolution. So maybe it's possible to just replace this linear layer by some convolutional layer, because if you use a linear layer, you will learn convolution, so maybe it's easier to put directly a convolution. And if you do that, you can have an architecture that are better trade-off. So it's quite interesting to use a general architecture at the beginning, and when you see which kind of operation are learned, just replace this block by the right operation, because it's more stable, because you don't have to, it's like a very strong regularization, because if you replace the linear layer by a convolutional layer, the network will definitely learn, will definitely do a convolution at this point. So it can be a good strategy to do that, to use the general architecture in the first time and just look at what is the result of the convergence and replace each layer by the right operation. So the question, is attention necessary? The answer is no. Splitting images in pages and training procedures seem to be the key element, because it's completely possible to train an MLP on ImageNet just by using the training strategy of transformers. Now the question is it possible for ConvNet to work with pages, and can they have similar property to transformers? Because something that is quite interesting with transformer is the attention map, because with attention map you can understand what are the key elements in the image, what are the patches related to the classification decision. For instance, here with VIT you can see the network focus on the animal on the image. But as you can see, the attention map here are a little bit noisy because we have to do a lot of average between the different heads of the multi-head self-attention, and there is self-attention at each layer, so we have to do an averaging across all the layers. But it's possible to have this behavior with ConvNet. You have just to replace the last average pooling by self-attention operation, and by just a single head self-attention operation. So we do that. We learn that learn aggregation. If you do that with resident 50, it works quite well. But as you can see, there is an artifact here, and you have this artifact on all the images. This is related to the pooling operation in ResNet. So there is not really an alignment between the pages and the final pages just before average pooling. So maybe it's not super optimal to have a very good attention map. So we propose a new CompNet architecture. This is an architecture without pooling in order to avoid this kind of artifact, with just one self-attention operation with just one head at the end of the network instead of the average pooling. And as you can see, you have less noise in the attention map and less artifact. And it's quite interesting because you can see what is the main component of the image. And you can go further and just try to use one class token by classes in the ImageNet dataset. Thanks to that, you can have an attention map by classes, and just with supervised classification loss, you can at inference time have this kind of weak segmentation. So it's quite interesting behavior. In particular, when you want to understand why the network make some kind of classification. For instance, if you look at the first images, the top one label is gross restore. And why we have this label? Because the network focuses on different fruits. But if you look at the second more important label in this image, it's orange. And why we have this label? Because there is some orange in the image. And this is the same thing with the Granny Smith. With the second images, it's quite interesting because you can see there is a lag side and there is also a valley. So possibly with these images, we can have different ImageNet labels, but on the ImageNet dataset, there is just one label by images. So sometimes we think the network is wrong, but it's not wrong. This is just the labels that are not very accurate. So, is it possible for CompNet to work with patches? The answer is yes. Can they have similar property to transformers? And the answer is also yes. We have just to add a simple learn aggregation module. Now I will talk a little bit about architecture and training interaction. The question is, does the training design matter as much as the architecture design? Because if you look at the ImageNet state-of-the-art model across the year, generally everybody knows AlexNet, ResNet 50, GoogleNet. So we focus a lot on the architecture, but generally when there is a new architecture, there is a new training procedure, and some part of the gain is related to the training procedure, but we just focus on the architecture. The ResNet is a quite interesting architecture. Currently, it's the most usual baseline used in the different paper. For instance, if you propose a new architecture, generally you have to do a comparison with the ResNet 50 architecture. So in this paper, we focus specifically on this architecture, and we try to understand what is the most important component when you take into account the accuracy of a given model. Clearly there is architecture, but there is also the training procedure and some noise in the measurement. Because on ImageNet, there is no separate test set, so there is some risk of overfitting, and we have to take this into account. So first, if we look at the different ResNet 50 results available in the literature, generally people report the result of ResNet 50 in the PyTorch library, so 76.1, but some other people report the ResNet accuracy in the original paper. But since the ResNet paper, there is a lot of new training strategy, and it's possible to apply this training strategy on ResNet to improve the architecture, and maybe it's the time to revisit the training strategy of ResNet, so we try to do that. We start from the training strategy we use in DIT, and we readapt a little bit in order to train some good ResNet. So we propose 3 different training strategies, A1, A2 and A3. The goal of A1 is to have the best possible model. A2 is to have a quite usual training strategy with 300 epochs. It's similar to the DIT training strategy, and DIT training strategy is usually used for transformer, so it's quite similar to classical training strategy on ImageNet. And A3, it's a shorter training in order to have a fast training. It's more similar to older training strategy on ImageNet in terms of number of epochs. So the first idea is to try to understand the interaction between the architecture and the training. So first we say, okay, we want to compare ResNet 50 and VIT. So VIT is a transformer architecture. And we take the A2 training procedure. A2 is designed for the ResNet 50 architecture, and we have this result on ImageNet. So here the conclusion is, okay, ResNet 50 are better than VIT small, and this comparison seems to be fair because we use exactly the same training procedure. But we can do exactly the opposite, design a training procedure for VIT small, and train the two architecture with this training strategy, and we can have the opposite conclusion. Here, VIT small is better than ResNet 50, and the comparison seems to be fair because we have exactly the same training procedure. So there is clearly some interaction between the architecture and training procedure. Maybe the best way to compare two architectures is to use the optimal training strategy for each architecture, but in practice it's very difficult. Because it can be very prohibitive because you have to do a lot of research with a different architecture, and it can be being very hard to know if the conclusion is robust because maybe in the future with the new training strategy the conclusion can completely change. So generally when we have some conclusion, it's just valid given some training strategy. Now we focus on the noise in the measurement. So on ImageNet, there is no separate validation set, and we do all the experiment with seed 0. And as you can see, with seed 0 we overfit a little bit because we do all the ablation with seed 0, but we run with 100 different seeds the ResNet 50 training in order to see what is the mean over this 100 different seeds and what is the standard deviation. And as you can see, we have this mean and this standard deviation, so there is clearly overfitting with seed 0. So if you do a lot of grid search, it's a good practice to do a multi-seed experiment in order to verify the level of overfitting and in order to understand if the conclusions are robust and what is the level of fitting of the hyperparameter search. So at the question, does the training design matter as much as the architecture design? The answer is yes. Training ingredient has a very large effect on performance, possibly more than the architectures. Now the question is for vision transformer. Maybe for vision transformer it's a more important question because transformer it's a very general architecture. With the self-attention mechanism we can learn some kind of convolution or we can learn some kind of long-range interaction. So you have a kind of architectural search in fact. You have just to find the right training strategy in order to learn the right operation. So we try to understand what is the impact of the training with transformers. So here this is result on ImageNet 1K and result on ImageNet 1K with different training strategy from the literature for transformers. And as you can see, the impact is very important. You can have very big gap between different training strategies, even when you have a lot of data like an ImageNet in 1K. And generally this result transfer to other tasks. For instance, if you reuse the previous model on semantic segmentation, you can outperform a more advanced architecture with just a simple VIT trained with a better training strategy. For instance, here VIT is better than Swin. Swin is a more advanced architecture, but here, just by focusing on the training strategy, we are able to have a better VIT architecture. In order to propose this new training strategy, we just revisit some simple components of the original training, because there is a lot of previous research on data augmentation for .NET. For instance, AutoAugment was designed for .NET, and maybe there is an overfitting of this data augmentation strategy in the .NET architecture. So we try to simplify the data augmentation for Transformer and try to design a kind of data augmentation for Transformer. In self-supervised learning, Transformers are usually very good, and in self-supervised learning, they use some kind of data augmentation like that, Gaussian blur, grayscale, and solarization. So during the training, for each images, we just select with a uniform probability one of these data augmentation. And in practice, it works better than more advanced data augmentation like AutoAugment. For the data augmentation, we adapt the data augmentation according to the size of the data set. For instance, a lot of people use random resize crop. So with random resize crop, you select a smaller crop in the image. It allows to have more diversity with just one images. But as you can see here, you can introduce some kind of noise. Because, for instance, if the label of the image here is zebra with random resize crop, you can completely remove the important object in the image. This is not the case with the simple random crop. With the simple random crop, you have just a sliding window with the image with a bigger crop. So there is less diversity, but also less risk of introducing some noise. So when you have a lot of data, like Imagine 21K, it's a better strategy. We do an evaluation of the overfitting, and as you can see, the new method is in orange, and it doesn't overfit more than other method, and in particular in Imagine 21K it overfit less, because when you have above this curve, you overfit less, and here you overfit more on the Imagine validation set. Now the question is, its training strategy is orthogonal to the architecture, and the answer is no. For instance, if you apply this training strategy on Swim Transformer, you don't have any improvement. So now we have a classical VIT better than a Swim Transformer just by readapting the training procedure. So now it's not clear if Swim is better than VIT. Because if you use a better training strategy for VIT, you can have better performance than Swim. And if you reuse this training strategy with Swim, it doesn't work. So it's not clear. Maybe there is a better training strategy for Swim, or Swim is overfitted on the VIT training strategy. So it's hard to know if your conclusion is robust, because you have to try a different training strategy, but in practice it's not generally the case. So the answer in for Vision Transformer, the answer is yes, the conclusion is the same, and the training is perhaps more important with Transformer architecture. In conclusion, taking into account the training taste discrepancy is possible by just adjusting the training, and it allows to exploit a useful feature at test time. There is a lot of other kind of train taste discrepancy, for instance the resolution. You can train a lower resolution and just fine-tune the network at higher resolution at test time in order to have a better performance, but by having a cheaper training. Architecture for computer vision can be very diverse with their own property. So you can use transformers, you can use ConvNet, you can use MLP. There is strong interaction between architecture and training. So you need to find the right training for the right architecture, because this can completely change the conclusion you have for a given architecture. So measuring the progress is a noisy process and can hardly be perfect. So we have a lot to do with the training, and generally we focus a lot on the architecture, but I think it's important to also take the training into account, because maybe with Transformer it's a quite interesting part. For instance, if you look at the NLP field, in fact, that doesn't change a lot the Transformer architecture. Maybe they change a little bit the activation and change a little bit the position encoding, but they typically keep this very general architecture and just focus on the data and focus on the training. So maybe it's the most important thing to do with this transformer architecture in computer vision. Thanks.
So you seem to say, I mean, all the evidence shows that training procedure is very important. So for a given new paper, how do we know that the paper is good because of thanks to its novel idea, or because of modern training procedure?
It's a very interesting question. I think it's important to focus on the ablation in that case in order to see, okay, with this given training strategy, we can have this improvement by just adding this new component. Generally in paper there is two parts, and unfortunately the most important part is to show how they build other architecture, but I think the most important part is the ablation. Unfortunately sometimes the ablation is not very well detailed, but yeah, I think it's a good idea to show an ablation if you propose a new method that is quite a bit orthogonal to the training strategy. You can try to use different training strategy to show that the method give a boost in that case. But if you want to use one training strategy, maybe the best is to use the best possible training strategy for a given architecture, and to show on this optimal training strategy, the method is able to give a boost. Because there is two kinds of paper. There is the paper that use a weak training strategy and that show in the ablation that the method give a good boost, but you don't know if this good boost transfer with a stronger training strategy, because when you have a stronger training strategy, generally it's quite harder to improve the performance of the model, because maybe there is some kind of like overfitting of the training procedure with the previous architecture. And in another side, you have some paper that merge the new method and the training procedure, and they don't do a real ablation. So in that case, it starts to know what is the gain related to the method. So the best is to do an ablation with the strongest training strategy in order to show that the new method is able to give a good boost on this very strong strategy, and maybe also try to use other architecture to see that the method transfer on other architecture, and if possible try other training strategy in order to show that the method is good with other training methods.
Is there a survey of perfect, I mean not perfect, but best training procedure available?
Good question. I don't think so. Maybe the best is to read some paper and try to see, maybe the best is to read some papers that focus on the training strategy. So currently for VIT models, maybe the best is to read DIT3, so the paper are present here. We have a new paper that improves that, so you can look also this paper. You can look at on my scholar the last paper that improved a little bit this strategy. But yeah, the best way is just to look at for table with state-of-the-art result with very simple architecture. For instance, VIT or ResNet 50, and try to see what is the best training strategy for this architecture. But in fact, there is no big change in the training strategy across the paper. Generally, this is some small adjustment, so it's not too hard to find a quite good training strategy for a given architecture.
In the slide, the annotation maps, you come back to it, please.
This one, or?
Yeah, the other one. So, if I understand well, you made some modification to ResNet 50 to bring attention. So, what did you exactly do to have attention in ResNet 50?
Yeah, so I completely removed the average pooling. So before the average pooling, with the ResNet 50 at resolution 224, you have a feature map of 7 by 7 by 2048. 7 by 7, this is a spatial dimension, so you can see that like the small images of 7 for height, 7 for width. So we apply with that a self-attention with a class token. So do you know how work self-attention? Yeah, okay. So you have the class token in the query, and in the key and the value you have the 7 by 7 pages, and with the class token in fact here we look at just the attention map, so we do the dot product between this class token and the 7 by 7 pages, we apply a softmax, and we look at the weight of this softmax. So you have, so in fact, in the class token, you have a weighted aggregation of these pages. The weight are given by the softmax, and you give that to the classifier. So, in fact, the input of the classifier, it's a weighted ponderation of these pages, and pages with a more important weight have a more important impact in this averaging, so maybe a more important impact on the classification decision. Therefore, we conclude it's patch more related to the classification decision. And we have, thanks to that, this visualization.
I think I need to look at the paper to get it more clearly, but I get your idea.
Have you considered class activation map techniques actually? Like they are usually a bit more, feels a bit more common in vision models, convolutional at least.
In fact, with class activation map, you have to add an additional step after the training. Here, this is directly integrated in the architecture, and it's easier to extract the attention map. But it's definitely possible to use a class activation map and all the different CAM variants in order to do that.
So you were talking a bit earlier about the evaluation. I agree it's very important, but I'm curious, like, where should it stop? Because in some sense, like, there is a bunch of tricks, trainings, and difference in architecture that go on. So as you mentioned, ResNet has gone through a lot. And so where should you stop to give proper understanding to the reader and the researcher about what is actually key, especially in your context? Because ablation techniques are talking about training strategies, sometimes about architecture, but you can also add the dataset dimension, perhaps in respect to the talk. So perhaps some strategies and tricks are actually completely biased to the dataset, some other aspects of the dimensionality is published.
Yes. Therefore, it's quite interesting when the ablation is done on different tasks or on different datasets. And generally, for the ablation, it's good to start from a well-known method. For instance, if you propose a new component or a new transformer architecture, maybe there is no lot of step to start from a classical transformer like VIT and go to this new architecture. And in parallel, you can do evaluation on ImageNet, evaluation on semantic segmentation. It's quite interesting if you have different tasks in order to see if the improvement is general or if it's just a bias on some task. Yeah.
Okay. Thank you, Hugo. Well, thank you a lot for being here. That's it for the talks. We apologize for the noise at the end because we took a long time. People started investing the bar, so sorry about that. But the perks of being in a bar is that you will have like charcuterie and cheese platters in the room, in the next room. So don't hesitate to take some, take a beer and talk to the speakers and anyone you like. Thank you very much.